So this is number theory. Lecture 4. And so you asked about a problem.
Problem 8.
On page 14.
I think so. I don't know the page. So,
With n factorial plus 1 and n plus 1 factorial plus 1.
yes, that one.
Okay. So let's take a look at that. So this is on page 14. So this is chapter 1, section 1.2. And exercise 8. And exercise 8 says to prove that two integers, n factorial plus 1 and n plus 1 factorial plus 1, are relatively prime for all positive integers n. This sort of boldface n means the set of positive integers. So a good strategy, if it's not obvious what to do at the very beginning, is just to look at the small cases. So suppose n equals 1. So n factorial plus 1 is 1 factorial plus 1. 1 factorial is 1, so 1 plus 1 is 2. And n plus 1 factorial plus 1 is 2 factorial plus 1, which is 2 plus 1, which is 3. And the greatest common divisor of 2 and 3 is 1. Right? This is our notation for the greatest common divisor. So it's true for n equal 1. What about n equal 2? So n factorial plus 1, 2 factorial plus 1 is 2 plus 1, or 3. N plus 1 factorial plus 1, 2 plus 1 is 3, so this is 3 factorial plus 1. 3 factorial is 6, 6 plus 1 is 7, and the greatest common divisor of 3 and 7 is 1. What about n equal 3? So 3 factorial plus 1, we just saw, is 7. 4 factorial plus 1. 4 factorial is 1 times 2 times 3 times 4. That's 24 plus 1, or 25. And 7 and 25 are relatively prime. Let's do one more special case. N equal 4. So 4 factorial plus 1 we just saw was 25. 5 factorial plus 1. What is 1 times 2 times 3 times 4 times 5? It's 120. That's 121. 120 plus 1. And if you look at 25 and 121, their greatest common divisor is also 1. So at least for the simplest, smallest cases, n equal 1, 2, 3, and 4, it's true. So this gives us some confidence that...
Wait, can I see the other page?
Sure. This is just working out the smallest cases.
Okay, I got it.
So what about, so we must prove the general case. That means the case for all positive integers n. So remember, n factorial is the product of all the integers up to n. N plus 1 factorial is the product of all the integers up to n plus 1. But this is the product of the first n integers times n plus 1. So n plus 1 factorial is n factorial times n plus 1. So I want to look at, I'm looking at the numbers n factorial plus 1 and n plus 1 factorial plus 1, which is n factorial times n plus 1 plus 1. So how do I prove that these are relatively prime? So let's just experiment. Suppose D divides both of these numbers, n factorial plus 1 and n factorial times n plus 1 plus 1. So if it divides two numbers, then D divides their difference. It divides n factorial times n plus 1 plus 1 minus n factorial plus 1. So if you subtract, the ones cancel. This is n factorial times n plus 1 minus n factorial. And if I factor an n factorial out of this, this is n factorial times n plus 1 minus 1. So this is n factorial times n. Let's see. What can we say about that? Actually, what I wrote is correct, but I might have a better way to do this. So let me start again. Suppose D divides n factorial plus 1 and n factorial times n plus 1 plus 1. So if D divides a number, and remember, what does divisibility mean? D divides a number k if k is D times q for some integer q. So if you say one number divides a number, it means it divides with the 0 remainder, divides exactly. So D divides n factorial plus 1. Write this on a big piece of paper. So if D divides n factorial plus 1, this implies D certainly divides n factorial plus 1 times n plus 1. Because D divides this evenly, so it's going to divide the product evenly. Which means, what is this? D divides n factorial times n plus 1 is n plus 1 factorial plus n plus 1. I just distribute this across. But we also are told that D divides n plus 1 factorial plus 1. Right? So this was given. D divides n factorial plus 1. So it divides n plus 1 factorial plus n plus 1. And it was also given that D divides n plus 1 factorial plus 1. So if D divides this number and this number, it divides their difference. So D divides the number n plus 1 factorial plus n plus 1 minus n plus 1 factorial plus 1. And when you subtract, the n plus 1 factorials cancel. N plus 1 minus 1 is n. So D divides n. So D certainly divides n factorial, because this is n times something. So therefore, D divides, it's given n factorial plus 1, and D divides n factorial, so D divides their difference. Which is 1. So D divides 1. But what are the divisors of 1? The only integers that divide 1 are plus 1 and minus 1. So D equals 1. So the only common divisor of n factorial plus 1 and n plus 1 factorial plus 1 is 1. So the greatest common divisor of n factorial plus 1 and n plus 1 factorial plus 1 is 1. That's the proof. Again, when we're asked to prove something, the proof is never unique. There can be a lot of proofs. This is one proof. And how did I find it? I said, well, when I started, I had no idea what to do. So I looked at some small cases just to make sure that it works. And then I experiment. But
another way that I did it was to subtract n plus 1 factorial plus 1 minus n factorial plus 1.
Right.
And then.
Right. So you said you took n plus 1 factorial plus 1.
Mm-hmm.
And from that, you subtracted n factorial plus 1.
Yeah, and then you
get n plus 1 factorial minus n factorial.
Yes.
Mm-hmm.
Then you take out the n factorial, you factor out.
So this is n factorial times
n plus 1 minus 1.
Right. So you get n factorial times n.
Yeah. That's another way of doing it, right?
Well, but but then what do you do next? I mean, this is a correct statement, but it doesn't prove yet what you're trying to prove. I mean, the difference of these two numbers is this. And you could say if D is a common divisor of this number and this number, then D divides this number. But that doesn't tell you yet that D is equal to 1.
Okay.
But this is a nice problem because you're forced to think a little bit about number theory and proofs in a kind of abstract way. And what we use in this proof is the following. We prove that if D divides K and D divides L, then D divides their sum and difference, say K minus L. Right? And the proof of this fact would be the following. If D divides K, that means K is DQ for some integer Q. And if D divides L, that means L is DQ prime for some integer Q prime. So therefore, K minus L is dq minus dq prime. If you factor out the d, you get q minus q prime. Q minus q prime is the difference of two integers. So it's certainly an integer. So therefore, d divides K minus L. So if you needed to prove that every divisor of two numbers divides the difference of the two numbers, this would be a proof. And if you wanted to show that d divides the sum of K and L, this would just be plus signs here, and the same result would hold. So I can make this plus or minus. Any other homework problems that I should do? So the last thing we did was look at the division algorithm or the Euclidean algorithm to find the greatest common to compute the greatest common divisor of two numbers, and to use it to calculate the simple continued fraction of the number. So let me look at just one more example of the Euclidean algorithm. And what are called simple continued fractions. So suppose I take the number 161 and the number 506. So let A equal 506 and B equal 161. So we use the Euclidean algorithm to solve three problems. So the first problem is compute the greatest common divisor of A and B. Let's call that D. Second, we prove that the greatest common divisor is always an integral linear combination of A and B. So we want to compute or find integers x and y such that D is written in the form ax plus by. And then the third is to compute the continued fraction for A over B. And what does the Euclidean algorithm tell us to do? It says take the bigger number and divide it by the smaller number. And look at the quotient and the remainder. So 506, if you divide it by 161, I think that's 161 times 3. So 161 times 3, I think, is 483. And 506 minus 483 is 23. That's the remainder. And then I take 161 and I divide it by 23. I think 23 goes into 161 7 times. Exactly, it leaves a remainder of 0. Wow. So this wasn't a very hard problem. So the greatest common divisor, so the last positive remainder is 23. So the greatest common divisor of 506 and 161 is 23. And in fact, this tells us that 23 is equal to 506 times 1, bring this over to the other side, 161 times minus 3. This is of the form 506x plus 161y, where x is 1 and y is minus 3. So here I've written the greatest common divisor is this integral linear combination of 506 and 161. And if I want to write 506 and 161 as a fraction, I get, just take this and divide. 506 divided by 161 is 3 plus 23 over 161, which is 3 plus. Now, if you don't know fractions, you better learn fractions somewhere. 23 over 161 is 1 over 161 over 23. And 161 over 23 is 7. So the simple continued fraction for 506 over 161 is very simple. It's 3 1/7. Okay. Any questions about that? Let me pick 2 more numbers and hope that the problem is a little bit harder to solve. Let's see. Just so no one thinks that this is fixed. Let's see. Someone give me a number, say a 3 or 4 digit number, any number you like. Either unmute and say it or just write it in the chat. Pick a number. Anybody there? Anybody have a number? 345. Okay. So let A be 345. I need another number, B. Someone give me another number? 643. Okay. So I want to find the greatest common divisor of these numbers and continue. So I can say take 345. Now, as it happens, this A is not bigger than B, it's smaller. But if I just do the first step, you'll see everything reverses. So 345, if I divide it by 643, it leaves a quotient of 0 and a remainder of 345, right? If you divide 345 by 643, the quotient is 0, and that's the remainder. So this really reverses everything for me. Okay, then I take 643 and I divide it by 345. So this goes in 1 time and leaves a remainder, I think, of 298. Okay. 345, if I divide it by 298, that goes in once and leaves a remainder of 47. 298, if I divide it by 47, this is like roughly like dividing 300 by 50. This probably gives me a quotient of 6. Let's see, 47 times 6, I think is 282, and 298 minus 282, this gives me a remainder of 16. So as I'm doing this, you should check my arithmetic because it's always extremely easy to make a mistake along the way. 47 divided by 16. Well, 16 goes into 47 2 times. And leaves a remainder of 15. And 16 divided by 15 has a quotient of 1 and a remainder of 1. And 15 divided by 1 has a quotient of 15 and a remainder of 0. So the last positive divisor, the last positive remainder is 1. So therefore, the GCD of 345 and 643 is equal to 1. Okay? So just go through carefully what I did and make sure it's okay.
Professor, why did you start with 345 instead of 645? 643?
Well, because whoever gave me the numbers gave me 345 first and 643 second, but I could have reversed it. I could have just started like this. Could you get the same result exactly?
Okay.
I mean, a better thing to do is start with the bigger number, but
Okay.
I mean, this just shows if you start with a smaller number, in one step you reverse the numbers, and it's the way you probably should have started in the first place.
Okay.
So now I want to find x and y such that 1 is 643x plus 345y. I want to write 1 as an integral linear combination of 643 and 345. X and y are integers. So I just work backwards from the Euclidean algorithm, and it looks like it's going to take maybe 5 steps. So first I have 1 is 16 minus 15 from this, which is 16 minus, and according to this, what is 15? 15 is 47 minus 16 times 2. So what I have is 16 minus times minus is plus. This is 16 plus 16 times 2. 1 plus 2 is 3. That's 16 times 3 minus 47. Or 47 times 1 if you like. But then I can write 16 as 298 minus this. So 16 is 298 minus 47 times 6. And I'm multiplying that by 3 minus 47 times 1. So if I look carefully at what I have, this is 298 times 3 minus 47 times 6 times 3. That's 47 times 18. And then 47 times 1. So this is minus 47 times 19. And then I can replace 47 by this difference. This is 298 times 3 minus, and what is 47? 345 minus 298 times 19. So what do I have here? I have minus times minus is plus. So here I have a 298 times 19 and a 298 times 3. That's 298 times 22 minus 345 times 19. And for my last step, 298 is 643 minus 345. So this is 643 minus 345 times 22 minus 345 times 19. So I have 643 times 22 minus 345 times 22, 345 times 19. That's minus 345 times 41, or 345 times minus 41. So that's equal to 1, if I did the arithmetic correctly. Let me just check. 643 times 22 is 14,146. 345 times 41 is 14,145. So that really is equal to 1, and everything checks. This is correct. So I have 1 as this integral linear combination of 643 and 345, where x is equal to 22 and y is minus 41.
Professor, I have a question. You started with 1 equals 16 minus 15. That's a 15?
Right. Here's my remainder 1. I write 1 is 16 minus 15.
Okay.
For this equation, I can write 15 as 47 minus 16 times 2. So I plug that in for 15 here. 16 minus 15. Or 16 minus.
So you start from the
47
bottom and go up. You start from the...
Yeah, well, there's no way you can do it otherwise. You can't start from the top and go down. You wouldn't get anywhere. You want to write 1 as a linear combination of the two numbers you started with.
Okay. And the way you get to 16 times 3 minus 47 times 1.
Then I substitute for the 16. I get this. I substitute for the 47. I get this. I substitute for the 298. I get this. And I'm done.
Where you get the 16 times 3? I'm still confused.
Here?
Yeah.
So I have 1 is 16 minus 15, right?
Mm-hmm.
But 15 is 47 minus 16 times 2. So for 15, I replace that by 47 minus 16 times 2. This is minus 47, and plus minus times minus is plus 16 times 2. And here I have a 16. So if I have 1 16 and 2 16s, that gives me 3 16. 1 plus 2 is 3. This is 16 times 1. This is 16 times 2. Put it together, you get 16 times 3.
Oh, okay. And then you take 298 minus 47 times 6. Yeah, 298.
That's what 16 is equal to. 298 minus 47 times 6. And then how do we work backwards to get the simple continued fraction? Let me just erase this line so I have a little more room. I have from my first equation, 643 over 345 is 1 plus 298 over 345. I'm just dividing everything in this equation by 345. And then I invert this fraction. This is 1 plus 1 over 345 over 298. So you have to understand how I got from here to here and from here to here. This is just fractions. So what is this? This is 1 plus 1 over, and according to this, 345 divided by 298 is 1 plus 47 over 298, which is 1 plus 1 over 1 plus And 47 over 298 is 1 over 298 over 47. So now I'm looking at this equation. This is 1 plus 1 plus 1 over 1 plus 1 over 298 divided by 47 is 6 plus 16 over 47, which is 1 plus 1 over 1 plus 1 over 6 plus 16 over 47 is 1 over 47 over 6. 47 over 6 is 2 plus 15 over 6. So I get 1 plus 1 over 1 plus 1 over 6 plus 1 over 47 over 6, which is 2 plus 15. Sorry, 47 over 16. 47 over 16 is 2 plus 15 over 16. 15 over 16 is 1 over 16 over 15, which is 1 plus 1 over 15. So this, let me write it on a nice piece of paper, perhaps. So I get this continued fraction, 643 over 345 is equal to 1 plus 1 over 1 plus 1 over 6 plus 1 over 2 plus 1 over 1 plus 1 over 15. So this is the simple continued fraction for 643 over 345. You work this out, this is exactly what you get. And in our notation for a continued fraction, we look at these numbers called the partial quotients. This is 1 comma 1, 6, 2, 1, 15. One, 1, 6, 2, 1, 15. This is how you solve this kind of problem. It's a very nice exercise in arithmetic. It's quite amazing what numbers pop up in these simple continued fractions. They really are very mysterious. 1, 1, 6, 2, 1, 15. And if you come back and you look at 1, 1, 6, 2, 1, 15.
You erased the 15, that's why. You erased it. No.
Oh, right, thank you, yes. This last one was 15 is 1 times 15 plus 0, that's the 15. Yeah. Okay, any questions about this? It's guaranteed on the first exam there will be a question that involves the Euclidean algorithm in computing a simple continued fraction.
So that means we're gonna do all these steps, all of these?
Yes.
Oh.
I mean, you have to be able to solve the problem.
If we find like the GCD and we cannot stop there, we have to like continue
Well, you have to solve the problem that's given. So if the problem is compute the greatest common divisor, you do that and stop. If the problem is to write the greatest common divisor as an integral linear combination of x and y, then you have to do this. If the problem is to use the Euclidean algorithm to find the simple continued fraction, then you have to do what I just did. That is, whatever the problem asks tells you what you have to do. It is, answer the question you're asked is the basic rule. All right. Okay, so now I want to begin section 1.4, which you can tell is important because the title of the section is The Fundamental Theorem of Arithmetic. Arithmetic is another name for number theory. So if something is called the fundamental theorem, you know it has to be important. And what the fundamental theorem tells us is something about how to write integers as products of simpler integers. It's just the way in chemistry you have a molecule, and every molecule is built up of atoms, and you want to find the atomic structure. So a water molecule consists of 2 atoms of hydrogen and 1 atom of oxygen, H2O. Carbon dioxide consists of, it's a molecule that has 1 carbon atom and 2 oxygen atoms. So the equivalent of atoms in number theory are what are called prime numbers. A prime number is an integer, it's called P, greater than or equal to 2. 1 is not a prime number. It's an integer greater than or equal to 2, whose only positive divisors are 1 and P. So for example, and a prime number and a composite number is an integer not 0. That is not prime. So if you start to make a table of the numbers, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. What can we say about these numbers? 2 is a prime. The only numbers that divide 2 positive integers are 1 and 2. 3 is a prime. 4 is divisible by 1 and 4, but it's also divisible by 2. So it's not a prime. It's composite. It's 2 times 2 factors. 5 is a prime. 6 is composite. It's divisible by 2 and 3, for example. It's 2 times 3. 7 is a prime. What about 8? 8 is divisible not just by 1 and 8, but also by 2 and 4. So this is composite. 8 is 2 times 2 times 2. 9 is composite. 3 times 3. 10 is composite. 2 times 5. And you can fill in the rest of this table. 11 is a prime. 13 is prime. 17 is prime. 19 is prime. 23 is prime. 29 is prime. And every other number on this list is composite. 12 is, for example, 3 times 4, or 2 times 6, lots of different ways. 14 is 2 times 7. 15 is 3 times 5. 16 is 2 times 2 times 2 times 2. 18 is 2 times 9. 20 is 4 times 5. Oh, and there are other ways to write it, and so forth. All these other numbers have divisors other than themselves in 1. So the prime numbers on this list are 2, 3, 5, 7, 11, 13, 17, and 19, 23, and 29. I think that's all. All the others are composite except number 1. Number 1 is just number 1. This is not prime and not composite. It's in a special class all by itself. So prime numbers, a positive integer that's prime or composite is at least 2, and this tells us what they are. So right now on a piece of paper, just for fun, compute the prime numbers, P, let's say I just went up to 30, maybe from 30 to 50. So make a little table and tell me what they are.
Wait, what did you vote on 1? What's that?
1 is not prime and 1 is not composite. 1 is special.
Okay. Wait, why is 9 not prime and 19 is prime, 29 is prime?
Wait, just 1 second, please. Nine's not prime because it's divisible by 3. Okay. The number is prime if it's only divisible by itself in 1, but 9 is divisible by 3, so it's composite.
Okay.
So what are the prime numbers between 30 and 50? What's the first prime number between 30 and 50? What could it be? What's the first number after 30?
31.
Very good. Is 31 prime or composite?
Composite.
What divides 31? What are the divisors? What's the number that divides 31?
One
Yes. What else?
and 31.
Right. And what else?
That's it.
That's it. So if the only divisors are the number 1 and itself, the number is prime. So the first prime number between 30 and 50 is 31. What's the next prime number?
33.
Well, what are the divisors of 33?
Oh, 3.
Right, so is 33 a prime?
No.
No, okay.
Um,
Else out there?
about 35.
What? What's the next prime number after
35.
31?
Oh, no, not 35. 37.
Yeah, 37. And what's the next prime after 37?
Um,
Of course, you can right away say to yourself, every even number is divisible by 2. So the only even number that's a prime is 2. Every other even number is divisible by 2 as well as by itself in 1. So no even number bigger than 2 is a prime. So you can just ignore the even numbers, just look at the odd numbers.
yeah. How about 41?
Good choice. That's a prime.
Okay.
Another?
43?
Yeah, 43 is a prime. And one more after that?
47?
Yeah. 45 is divisible by 5. 49 is divisible by 7. These are all the prime numbers between 30 and 50. Good. I mean, you could ask yourself, well, what about the prime numbers between 50 and 60? And you say, actually, how far do you go? Maybe at some point you run out of prime numbers. That is, maybe at some point you found them all. But one of the theorems we'll prove Wednesday or next week is the theorem that goes back to Euler. You actually find it in Euler in Greek 2,300 years ago, that the number of primes is infinite. No matter how far out you go, you can always find another prime. It's one of the fundamental facts about in number theory. Okay, actually, so Euclid proved that, but the first thing I'm going to do, the first step in proving what is the fundamental theorem of arithmetic, is something called Euclid's lemma. But maybe I'll start, but just by telling you, as like a preview of coming attractions, what is the fundamental theorem of arithmetic? FTA, fundamental theorem of arithmetic. It says that every positive integer can be written as a product of prime numbers. So this is just like in chemistry when they tell you that every molecule is a product of atoms. Every integer is a product of prime numbers, and the representation of an integer n, at least one, as a product of primes is unique up to the order or except for the order in which you write the primes down. For example, 6 is composite. And you can write 6 as a product of the prime 2 and the prime 3, or you could reverse the order. 6 is also 3 times 2. But no matter how you write 6 as a product of primes, there will always be 1, 2, and 1, 3 in one order or another. If you take a number like 240 and you write that as a product of primes, let's see, how can we do this? Actually, you can do what sometimes they do this in elementary school, and they call it a number tree. Just 1 second, please. They call it a number tree. Let's see, 240, maybe we write that as 2 times 120. And 120 we could write, I don't know, it's 3 times 40. 2 is a prime, you can't factor that. Maybe I'll write 120 in a more interesting way. It's like 6 times 20. And then 6 is 2 times 3, they're primes. 20 is 5 times 4, 5's a prime. But 2 factors into 2 times 2. So 240 is the product of the 4 2's, 2 times 2 times 2 times 2 times 3 times 5. So this is 240 written as a product of primes, but I could have done, I can write them in lots of different ways. 2 times 3 times 2 times 5 times 2 times 2. This is also correct. But again, if you look at this, you see you have 1 3, 1 5, and 2 4's. Or 5 times 2 times 2 times 3 times 2 times 2. I mean, there are lots of different ways to arrange the prime numbers that multiply out to give 240. But no matter how you write 240 as a product of prime numbers, there will always be 4 2's, 1 3, and 1 5. So this is the fundamental theorem of arithmetic, that every number is a product of primes, and except for the order in which the primes are written down, the product of primes is unique.
Professor, I have a question.
Yes.
Why you didn't include the 4, the 6, the 20, the 120?
Well, of course, when I got to 6, I'm trying to factor everything into a product of primes. 6 is not a prime, but instead of 6, I write 2 times 3.
Okay.
Right? Here I have 20 is 5 times 4. 5 is a prime. I can't go any further down a tree, but 4 I can. 4 splits into 2 branches, 2 and 2.
Okay.
And there are lots of ways you can draw these trees, but you always end up with the same result. So for example, suppose I take n equal to 100. So we're going to have a tree that goes like 100 is 10 times 10.
Oh.
But these factor, this is 2 times 5, 2 times 5. These are the primes. So 100 is 2 times 5 times 2 times 5. Or I could have done my tree differently. I could have said 100 is 4 times 50, 4 times 25. But these are both composite. 4 factors into 2 times 2, 100 factors into 5 times 5. And again, I have 2 2's and 2 5's. Or I could have factored as 100 is
2 times 50.
Sorry?
2 times 50?
Yeah, 2 times 50. 2 is a prime. I can't go any further beyond that. But 50 is, let's say, 5 times 10. And then 10 is 2 times 5. And again, I have 2 2's and 2 5's. Okay? So these are 3 different factorization trees for 100. But if you factor every branch until you just have prime numbers at the end, there are always 2 2's and 2 5's. 2 2's and 2 5's. 2 2's and 2 5's. Okay? That's the fundamental theorem of arithmetic. Here, there's an example for everyone to play with for a moment.
Someone wrote on the comment, not 4 times 5.
Let's see. What, I don't, where's the comment? Let me just check. 25, this is a 5 and a 5. 25 is 5 times 5. My handwriting is not great. Okay. Draw. Let's call it the factor tree for n equal to 6006. So just start factoring this number as a tree. You don't have to do it as a tree in general, but it's just a very visual way of doing it. And just go down every branch as far as you can, and you stop when a branch ends in a prime number. Then you can't go any further. So, anyone get a factor tree for this? You could start with 6006. It certainly factors into 6 times 1001. That's kind of easy. And 6 also factors into 2 times 3. And 2 and 3 are prime, so you can't go any further. But what about 1001? Is 1001 composite or prime? Let's see, it's not divisible by 2. You can check, it's not divisible by 3. You can see that it's not divisible by 5. What about 7? I divide 7 into 1001.
It's 143. 143.
Yeah, so this is 7 times 143. So 7 is a prime. What about 143? Is that a prime? Or is that composite? Not divisible by 2. It's not divisible by 3. Not divisible by 5. It's not divisible by 7. I'm just looking at the primes. Is it divisible by 11? The 11 into 143.
Yeah,
so
13.
Yeah, it goes 13 times exactly. So this is 11 and 13. And now we're done. We have 6006 is a product of 2 times 3 times 7 times 11 times 13. This is a product of 5 primes. Up to the order, the unique factorization of 6006 as a product of primes is 2 times 3 times 7 times 11 times 13. That's factoring this number into a product of primes. Okay. Well, the proof of the fundamental theorem of arithmetic, right? This is my assertion that the fundamental theorem of arithmetic states that every positive integer is the product of primes in a unique way. You could also include 1 in this. 1 is sort of like the empty product. It's a product of no primes. So if you want to say 1 is a product of primes, if you take a product of no primes and you declare that to be 1, that's 1. But it might be easier just to say every integer greater than or equal to 2 is uniquely a product of primes. And the first step in the proof of the fundamental theorem is a result that is also in Euclid called Euclid's lemma. It's really a major theorem, but it's called Euclid's lemma. And Euclid's lemma says the following. So in the text, this is theorem 1.7. It says, let A, B, and C be integers if A divides the product of the numbers B, C, and if the greatest common divisor of A and B is 1, then A divides C. So for example, look at that, A equals 7, B equals 3, and C equals 14. So 7 divides 42, which is 3 times 14. 7 divides BC. A divides BC. A and B are relatively prime. The greatest common divisor of 7 and 3 is 1. So if 7 divides 42, which is 3 times 14, but 7 is relatively prime to 3, 7 divides 14. This is a kind of example of what Euclid's lemma says. So it says if A divides a product of two integers, but is relatively prime to 1, then it must completely divide the other.
Where you got 42?
3 times 14 is 42.
Okay.
This is B times C. 3 times 14 is 42. So 7 divides 42, which I can write as 3 times 14. 7 is relatively prime to 3, therefore 7 must divide 14, and of course it does. 7 times 2 is 14. So how do we prove Euclid's lemma? This is a very important proof to understand. So if A and B are relatively prime, that is, if the greatest common divisor of A and B is 1, this implies there exist integers, x and y, such that 1 is ax plus by. The greatest common divisor of A and B is an integral linear combination of A and B. We're given that the greatest common divisor of A and B is 1, so there exist integers x and y, such that ax plus by is equal to 1. Now, we're told that A divides BC. Let's multiply this equation by C. You get C is equal to ACX plus BCY. I just multiply this equation by C. But we're also told that A divides BC. So BC is A times Q for some integer Q. So let me substitute this for AC. So C is ACX, and I can write BC as A times Q plus AQY. And all of these letters represent integers. A, B, C, X, Y, and Q are integers. From this, I can factor out an A. A is CX plus QY. Now, what does this say? A, that's C, is A times this integer. That's exactly the definition of divisibility. A divides C. And that's what we needed to prove. So this is exactly the proof of Euclid's lemma that's in the text, which you should be looking at. So on page 26, it's all there and legible as well. And we can draw some conclusions from this right away. So this is a kind of a corollary. We have integers A, B1, and B2. If the greatest common divisor of A and B1 is equal to 1, and the greatest common divisor of A and B2 is equal to 1, then the greatest common divisor of A and the product B1 times B2 is also equal to 1. So if A is prime to two different integers, it's also prime to their product. And the proof is essentially a proof by contradiction. Let D divide both A and B1, B2. So D, if divides A and B1, B2, so B certainly, D divides A. And it's given that, let's see, D divides A, because A, let's see, how do I want to say this? So D divides both A and B1 and B2. So D divides A and D divides B1, B2. D divides A, and so D and B1 must be relatively prime. Let's see, why is that? So I have A and B1 have no common factor. D divides A. If D divides B1, then D is a common divisor of A and B1. But the greatest common divisor of A and B1 is 1, so D can only be equal to 1. So D is relatively prime to B1, and D divides B1 and B2. So again, let me just repeat this. D divides B1, B2, and the greatest common divisor of D and B1 is 1. So by Euclid's lemma, D divides B2, which means D is a common divisor of A and B2. But the greatest common divisor of A and B2 is 1, so D has to be equal to 1. So if D is relatively prime to two integers, it's relatively prime to the product. And a consequence of this, which will be the first thing I prove on Wednesday, is, it's in the text, this is theorem 1.8. We have integers A, B1, B2, B3 up to B sub k. It's a finite set of integers. If the greatest common divisor of A and B sub I is 1, for all I going from 1 up to k, that is, if A is relatively prime to each of these k integers, then A is relatively prime to the product B1 up to B sub k. So this is a consequence of Euclid's lemma. So if you have k integers and A is relatively prime to each of them, then the integer A is relatively prime to the product. So this is what I will prove on Wednesday. And again, let me remind you that, see, I had an office hour problem session yesterday. There's one also this evening at 7 o'clock. So if you have questions about any of the material or questions about any of the homework problems, even the problems that are due today, just please log on at 7 and ask your questions. And that will be it for today. Any questions before we stop?
You didn't post homework 3 yet, right?
Correct. I'll post that today.
But that will be due for next week, not this Wednesday, right?
Oh, no, the homework is generally due on Mondays.
Okay.
Next week, there's no school on Monday, so it'll be due on Tuesday.
Oh, next week is
No, sorry, not next week.
next
No,
week.
next week we have school on Monday. The week after that, there's no school on Monday. So, yeah, so the homework for the next homework, there's a homework due today, and the next homework will be due next Monday.
Okay. And for the midterm, roughly how many questions will be on the midterm?
I don't know. It's 5 or 6 or 7 usually. You know, I haven't made it up yet, so I can't tell you yet for sure.
Okay, but not more than 10 though.
Oh, no. It's a relatively small number. And there's always like extra credit, so you can leave out a problem and still get 100 on the exam.
I'm sorry?
There's always like extra credit, so if you leave out a problem, you can still get 100 on the exam.
Oh, okay.
But if you leave them all out, you get a 0. So
Yeah.
it's not that good.
All right. Thank you.
Okay.
See you. So
All right. See you possibly this evening. Otherwise, next class.
no, at 11 because I have you for 11.
Sorry?
At 11 o'clock.
Okay. Well, I was talking to the class, not you personally.
Okay.
Okay. Okay. Bye, all.